Okay, so thank you everyone for coming who's made it. So today we have, I guess, our first talk on verified compilers of any kind. There'll be a few more coming in the next couple months. And so we've got Eske from the University of Aarhus, and I guess Input Output and Inria as collaborators on this project. And he's going to talk to us about Peregrine, which is a verified middle end for code generation from proof assistance and ties into Rocq. So Eske's done a bunch of different work in Rocq on smart contracts and digital exchanges, and now obviously certified compilation. And so I'll let you take it from here.
Yeah. So I'm Eske, and I'm going to talk to you about Peregrine today. And yeah, as you said, I've worked previously on smart contract verification, and as you all know, there's been a lot of work on verifying smart contracts in proof assistance, and often that verification is done on embeddings or re-implementations in the proof assistance, which of course leaves a unverified gap. So right now I'm looking at how we can use verified extraction from proof assistance to close this verification gap. So today I'm going to talk about Peregrine, which is a verified middle end for code generation from proof assistance. So there's been a lot of efforts in most proof assistance to implement both verified and or unverified proof extraction, code extraction from proof assistance. For example, in Hull, they have a verified compilation to KGML, which also has a verified compiler. So you have instant verification of extraction in Hull 4. Similarly, in Lean, they come with a built-in compiler to C, which is unverified. Similarly, Agda has extractions to both Haskell, JavaScript, and Rust, also unverified. On the Rocq side, there's, for example, the CompCert verified compiler, Certicoq, which has verified extraction to C, which hooks into CompCert, so you can get fully end-to-end verified code. Similarly, there's verified extraction to Camel and WebAssembly, and also a bunch of unverified extractions from Rocq. However, there's a lot of duplicate work because implementing extraction to every single language in existence for every single proof assistant is a lot of duplicate work. Also, most of these extractions don't really have a common interface, which makes it hard to sort of switch from one to another or use multiple backends to be able to extract to multiple languages. And also, most of these works have very similar intermediate languages and similar passes throughout their pipelines. So that of course raises the question of why can't we share some of this, make it a bit more unified? So that is what Peregrine tries to do. So Peregrine is a middle end for extraction from proof assistance, which serves to have a common set of passes, optimizations that you can do on this intermediate language called LambdaBox, as well as a common interface for front ends and back ends to hook into this pipeline. So currently, the framework has 3 front ends: a verified Rocq front end, and an unverified Agda front end, and an unverified Lean front end. So these front ends produce LambdaBox programs from Rocq, Agda, and Lean programs. And these programs can then be extracted from the proof assistance, piped into the middle end, which then does a bunch of micropasses that both change the semantics of LambdaBox slightly, but also optimizes the program to make it match whatever the backends expect. And then the middle end passes the optimized transform program onto the backends, which then compiles it to the target language, which currently the target languages that are supported are OCaml, C, and WASM, which are verified, and then Rust, Elm, and KGML, which are unverified. And the Octa and Lean front ends, as well as the KML backends, are new contributions of this work, as well as the middle end. Whereas the Rocq front end and the remaining backends are all pre-existing work. So Lambda-Box, as I mentioned, is an intermediate language used in Peregrine. It was initially introduced by Nielsen as a target language for type and proof erasure from the calculus of inductive constructions, which Rocq is based on. Similarly, it was used to implement the first code extraction in Rocq, which targeted Haskell and OCaml, which was unverified. The erasure part of the extraction pipeline was later formalized in Mesa-Rocq and verified. And this language is used in most of the extraction work in the Rocq ecosystem already. And extraction works in other proof of systems have very similar intermediate languages to Lambda-Box, which both Octa and Lean has. So Lambda-Box is a very standard lambda calculus with an added constructor, which is this box constructor, which represents erased terms. So during erasure, any proof relevant, non-computationally relevant terms are erased to the box term. It also has De Bruijn indexes, which is grel. It has variables and evars. These are just related to representing proof-related stuff. So these are not really used in the pipeline or any of the extraction backends. So they're just for example, extension variables in proofs. Then it has lambdas and nets and application, as well as constants to refer to defined constants that are in the environment. So as well as terms, we also have a global environment which contains constant declarations and inductive types. Then there's a constructor, as well as pattern matching cases and primitive predictions. And then we have fixed points and co-fixed points, as well as primitives, which corresponds to the primitives that are in Rocq, which are primitive integers, arrays, strings, etc. And finally, there's lazy and false, which are for lazy evaluation. By default, the evaluation in Lambda-Box is called by value, which the entire Mesa-Rocq pipeline is designed for it to be called by value. But there's also some interest in relaxing this and also supporting other calling conventions. Then there's the typed version of Lambda-Box, which also has type annotations on inductive definitions and type and constant definitions. So it's not fully typed. We only have typing on decorations and not everywhere in the AST. And so that includes type variables, inductive definitions, constants, application, and functions, as well as a type for the box constructor, and a T type, which corresponds to types that are not representable in the backends. So this is, for example, for dependent types, which the backends don't support. So these are just raised to any type representing that. So Lambda-Box is a completely standard lambda calculus with we call by value, as I said. However, due to this addition of the box constructor, we also have some additional semantics for it. So a box well, if a term evaluates to a box, then applying anything to that term, it also evaluates to a box. So a box just swallows anything you give it, which it's not non-computational part of the code, so just do whatever with it. Similarly, you can do pattern matching on boxes as well. So if A evaluates to a box and you pattern match on it, then you just choose the first branch of that pattern match and apply boxes to all the arguments of that branch. Similarly, you can also apply boxes to a fixed point, which just evaluates as that. Then there's also a limitations on constructors. So it's expected that constructors are not fully applied. Well, how do I say it? I lost my train of thought. So during the pipeline, Peregrine does this transformation where it expands constructors to be fully applied. So a requirement on the lambda calculus is that they are fully expanded as such. So the middle end, as I said, is comprised of a bunch of microparsers. Some of them just change the semantics of the program, of the language, whereas some of them are to lower the program into a subset of lambda box that matches whatever the backend expects, whereas some of them are just to purely optimize the program. So to communicate between the front ends and the back ends, we implemented a verified S expression parser and printer. So the front ends produces lambda box in S expression form, which the middle end then deserializes, performs all the passes, and then it serializes it again into S expression form and passes it on to the back ends. So the first step, as I said, is deserializing it. Then it performs some validations. So previously, it was just proven that all the lambda box terms put into the backends were correct, because the only consumer of lambda box terms previously was Rocq, which was verified. So you all knew that you had a proof that all the terms produced by Rocq were verified. Question. So the blue text in this diagram is your question, right? So the blue text is new additions to the pipeline. So the ones that are not in blue are things that come from the existing backends, whereas the ones in blue are things that are new. And the ones with a star are unverified at the moment. So yeah, previously we just knew that programs were the lambda box terms we got were always well-formed and correct. However, the lean and Agda front ends are not verified, so we add a step to check that the programs we get are actually valid, and that is that to be valid, it means that the program is well-formed and that the extraction configuration actually matches what the backend expects. After that, we have a name sanitization pass. So again, this is new because previously Rocq was the only front end, and in Rocq you can have Unicode characters and weird stuff in identifiers, but it's not very common. So it was not something that anyone had thought of doing. However, in Lean and Okta, it's much more common to use Unicode characters in your identifier names, which in most languages is not valid. So we need to do a sensitization pass to make sure that all names are valid in the chosen backends. Then we have a constructor reordering pass, which is necessary because sometimes you want, for efficiency, you want to map some type in the front end to some type in the back end. However, it might be the case that the order of the constructors doesn't match what it is in the back end. For example, in Rocq, the first constructor in a Boolean is true and then false, whereas in OCaml, it's false and then true. So we have a verified pass that reorders these constructors to match what it expects in the backend. Then there's a pass that changes the semantics of recursion functions to always unfold. Similarly, we have a pass that removes parameters because parameters are in the untyped lambda calculus not computationally relevant. So we can just remove them. For example, here in this example, we have the case where we have a constructor. This is the zeroth constructor of the list type, so that is the empty list is how you read this. And this is applied to a T-box because the list is polymorphic, so it has a type parameter. However, this type parameter in the untyped lambda calculus is not necessary, so this pass removes it, and then also removes the application of box. And box here is the erased type parameter. So I guess if this example had been a Boolean list, then this would have been bool, but it was erased to T-box. Next up, we have a pass that removes matches on anything that's not computationally relevant. So for example, if you had a match on some A that lives in prop, so it's not computationally relevant, then we can just erase that match by substituting B for box in the branch C. And here C is just the first branch because it's not computationally relevant. Next up, so we have a de-arcing pass. So because you have a lot of both polymorphic definitions in your source, in your persistent source, you also have a lot of other proof irrelevant things or computationally irrelevant things. You get a lot of boxes in the produced lambda box terms. And most of these can be removed. And to do that, we have a dead argument elimination pass. Of course, it also removes things that aren't boxes, but the main motivation for having it is removing all these unnecessary boxes that gets added from erasing things. So for example, if you had a function that had 2 arguments that doesn't occur in the body, then these would get removed. Then we have a pass that inlines predictions. So this is those that are not familiar with Rocq, this might be a bit weird. So in Rocq, there are several kinds of predictions. There's those called primitive predictions, and then there's normal predictions. Normal predictions are just functions that do pattern matching to get whatever variable you're doing a prediction to. whereas primitive predictions is a primitive function that does this prediction. So, and these primitive prediction we erase into just being the pattern match. So for example, if we had a pair defined as a record with primitive predictions enabled, then we had some function foo, which takes a x of type pair and then returns the first prediction. Then this would get erased into a pattern matching on x with where we match on the prediction here on the constructor and then return the element. Then, as I said earlier, so in lambda box, we expect that constructors are fully applied. So we have a pass that does this. So it takes and fully applies all constructors so that it's always a fully expanded to. Similarly, most backends, well, not most, all the backends don't support co-fixed points, co-induction. So we have a pass that translates these co-fixed points to standard fixed points plus lazy evaluation. So this is just adding lazy in front of all constructors and then forcing it whenever you're pattern matching on it. Then we have an optimization for singleton types. So if you have some inductive which just has one constructor with one argument, then this gets erased. The type gets completely erased. So if we had this foo, which has one constructor bar which has one argument, then instead of wherever that constructor occurs, it just removes it so that it's just the argument. Then we have inlining and beta reduction passes. And then we have this inductive remapping. So one of the main limitations of program extraction is usually efficiency, because you often don't have efficient implementations or efficient types in proof systems. So you would like to be able to remap things to efficient implementations in the target language. So one thing that's not mentioned in this pipeline is remapping constants, because that's not handled in Peregrine, that's handled in all the backends separately, because that needs to happen right at the end of extraction. However, remapping constants is not always enough. We would also like to be able to remap types. So for that, we have added a new pass for remapping inductive types. So what it does is that, for example, if we had the nat type in the unary encoding of natural numbers, this gets remapped such that you add 4 new axioms, one representing the type, one representing each constructor, and one representing pattern matching, so an eliminator. And these are then remapped using the traditional constant remapping function that all the backends already has. And then the pass translates the pattern matching into applying the eliminator to each constructor, where nullary constructors are wrapped to avoid early computation. Finally, we have this box term, which represents erased terms. Box is not something that exists in any of the target languages, so we need to handle that some way. So we have a pass that implements box as a fixed point that just calls itself over. So it matches the semantics of box, that box just swallows anything you give it and gives back a box. Finally, we have a pass for implementing lazy, just as the way you'd expect it, by delaying commutation. And lastly, so as I mentioned earlier, so Lambda box has De Bruijn indices. The target languages don't have De Bruijn indices, so we of course need to add names back. So we have a pass at the end that adds names to all these indices. And then lastly, it gets serialized and passed on to the backends. Okay, so that was middle end. So how do you then get these Lambda box terms? So we have 3 front ends. The first one is the Rocq front end. So this is not new work. We just repurpose Rocq as a Rocq front end. So Rocq is a project formalizing the type theory of Rocq inside of Rocq. And as on top of that, they then implemented a verified proof erasure. And we then repurpose that to produce Lambda box terms and type Lambda box terms. And this work is verified. So we actually get a proof that the Lambda box terms are both well-formed, but it also has the same computational semantics as the original Rocq term. As one thing I didn't mention earlier is that as well, so for the pipeline here, so most of these passes are verified, and we have a proof stating that if the Lambda box term given in the input is well-formed, then the resulting Lambda box term after all the passes is also well-formed and computes to the same thing. Of course, we have the proof, but as you can see, there are a few passes that are trusted. So those parts, you of course have to trust that. Then we also have a new Agda frontend. So Agda's internal representation is quite close to Lambda box, except for a few differences which we have to handle. But besides that, the translation from Agda to Lambda box is quite straightforward. It's based on the Agda treeless pipeline, which is a step that transforms this internal representation to another very similar representation so in Agda you can do basically pattern matching when you define functions. So you can say if you have like an argument that's a natural number, you can say if this argument is 0, then use this definition of this body for the function, and if it's 1 plus something, use this function body. And this representation is kept in the Agda internal representation. So this treeless pass pipeline takes this and transforms it into the usual definition you'd expect, where a function just has 1 function body. So it basically inlines the pattern matching that is done into the function body. But even with that transformation, there's still 2 edge cases where we need to do an additional transformation to actually make it match with Lambda box. The Agda frontend is written in Haskell, and it hooks into the Agda compiler pipeline using annotations. So you annotate all the terms you want to extract, and then once you compile the Agda program, the backend gets called, and we extract those to Lambda box. So the first thing we have to be careful about is pattern matching. So for example, take this example where we have a function that takes the head of a list. And usually you would, like one way you'd usually define this is just return an option or maybe type if so that you can handle the case where the list is empty, or you'd have a default element. But in this case, it's defined using a proof that the list is non-empty. So there's only one branch in this constructor corresponding to the cons case where the list is not empty. However, in lambda box, we expect all pattern matches to be exhaustive. So we have to sort of make up a case, a body for all the branches that don't exist. However, doing that is not completely trivial because it also needs to be well typed for it to be able to produce type lambda box. So one obvious choice would have been to just put in a box in all those branches which don't exist but are needed, even though we know that they shouldn't be reachable. However, this will not be well typed because box doesn't have the same type as list. So the solution for this is that we introduce this empty type, which doesn't have any constructors. And then for each branch, which doesn't exist where we have to insert, we just make a match on the empty type, which we know that can't happen. And then we match on box on that. So that way we actually get something that's well typed and also still know that we can't ever reach this case. The second thing we have to be wary of in the translation is mutual fixed points. So in lambda box, there are no mutual fixed points at the global declaration level. You only have mutual fixed points at the term level, so you can't have a mutually defined fixed point globally. So what we do is that for each mutually defined fixed point in Agda, we generate. So if we have two mutually recursive definitions, then we generate two global declarations, one corresponding to one fixed point and one corresponding to the other fixed point, where the opposite one is inlined into the definition. So we can see an example here for even. The body is a fixed point with two entries, one for the even case and one for the odd case. We also implemented a lean frontend for Peregrine. It's based on the LCNF representation in lean, which is a normal form lambda calculus. Just like the Agda frontend, it also uses these annotations to mark which definitions you extract, and then it hooks into the compiler pipeline and gets called whenever you compile your lean file. And we need to have just the same considerations for the lean front end, where we need to have a similar translation for matches and a similar translation for mutual recursion, because lean also has the same problem with, well, it's not a problem, but it has the same difference in their internal syntax. But other than that, their syntax is very close to lambda box, so the rest of the translation is fairly straightforward. However, with the lean frontend, there are also some performance considerations that we have to make, because in lean, the compiler relies very heavily on foreign functions for efficiency. So a lot of things, a lot of types and functions in lean are implemented quite inefficiently on purpose, because in the compiler it just gets replaced with an efficient primitive in C. There are also a lot of functions that have inefficient implementations, and then efficient implementations in Lean and then approve that they're equivalent, and then they get replaced during extraction. And it also uses extensive use of inlining for performance. So to also get somewhat performant code out of the Lean front end, we need to take care of these things. So the Lean front end supports both emitting all these things that are marked as foreign as axioms, which can then get remapped in the backend to get efficient implementation, but it also supports ignoring these foreign function annotations and just extracting the inefficient implementation as is if you want to have something that's more trusted. Similarly, there's this csimp pass in Lean, which replaces inefficient Lean functions with more efficient ones. So we also make heavily use of that in the Lean front end to get as efficient code as possible. And all the inlining annotations are also passed on to Peregrine so that they also get inlined in the backends. So the backends that we currently have is a C backend, which is based on Rocq. It compiles to C Lite, which is a subset of C used by the CompCert compiler. It is mostly verified. That is, it has a few passes that are not verified currently. And it also has a verified garbage collector. We also have a washing backend, which is also based on the Rocq pipeline. Again, the Rocq pipeline is not fully verified, so it has these trusted parts, but the extension to washing is fully verified and based on the WebAssembly 2.0 standard with tail calls added. It has a simple bump allocator and no garbage collection. However, there's also an unverified translation that has garbage collection. But yeah, as I said, it's unverified at the moment. We also have a camel backend, which extracts to the untyped intermediate language called lambda or camel. So we target something called malfunction, which is a formalization of the lambda intermediate language. It's proven correct for programs that don't use primitives and co-inductives. Then we also contributed a CakeML backend. So CakeML is a functional language based on standard ML, which is used in Hull. It has a fully verified compiler, and we can extract out-of-the-box terms to CakeML in its S-expression form. So we don't target the service language, but the service language has a S-expression form. So it's close to the service language, but yeah, it's not human readable code we produce. It's also untyped and it's not yet proven correct, but we have formalized the semantics of the subset of CakeML that we extract to. So we plan on proving it correct in the future. Then we also have extraction to Rust and L. Contrary to the other backends, this is typed. So we also get typing information for the extracted code, plus the extracted code for these backends is actually human readable, whereas the previous backends target either machine level like WASM or very non-readable C code like the Rocq pipeline, this produces something that's close to being as readable as the source in the proof of systems. However, it's not yet verified. And it doesn't have garbage collection, so on very memory-heavy programs, it's inefficient. Then I wanted to show just quickly a few examples of what it looks like. And it didn't switch. How do I share this? Here we are. So on the left, we have a Octa program where we can see we have a bools definition, we have not defined, and some other definitions on Boolean. And then we have a symbol test, which we then have annotated with the Octa box annotation, which means that when you compile this Octa program, the Octa front end gets called and produces a lambda box file, which you can then pass on to Peregrine. And this lambda box file looks like this on the right. This is the S expression form of lambda box, which we can then compile to WASM, where we get, as I said, it's not human readable at all, but it's decently efficient and also verified, which is, I guess, the costs you pay here. And we have the C version. On OCaml. And the same for KML and for Rust. Hope you can see it. It's not very big, but see, for Rust we get something that's a bit closer to looking like what the original code looks like, except of course you have for the nats, this of course we don't have the nice notation where here we can just write 42, where this is of course expanded to 42 applications of the one constructor. But besides that, it looks close to what the source code looked like.
If I can ask you a quick question about this, specifically with respect to Lean, but also respect to some of the other front ends you've added, because obviously, as you mentioned, Lean has this reliance on foreign functions in the C codes. Do you have rough benchmarks or just like a rough sense of what the performance difference is?
Yeah, so I have a bit about evaluation of it.
Perfect.
Here at the end, and I don't know, maybe a bit short on time.
We can go a bit over if there's more to say.
I don't have that much left to say. So the evaluation is still very preliminary. So we still have more stuff to evaluate, but we have successfully applied Peregrine on several industrial applications, larger scale industrial applications. So it shows that it is usable as it is now. We've also evaluated the front ends against each other to see. We would expect that the front ends would give similar performance on similar programs. And then we have some very preliminary evaluation of the backends. So evaluating the front ends, we have here a small test suite of standard programming benchmarks, so binary trees, quick sorts, that sort of things. And these programs were all implemented with taking care that the implementations are as close as is possible to each other. So we have an implementation of each program in each front end. And they're using no remapping, so not any efficient primitives, just the inefficient versions. You have to compare the front ends as much as possible. So we get that the front ends are quite similar on most examples. However, there are some differences. So the benchmark showed some limitations of both the Acta front end and the Lean front end. So for the Acta front end, in the internal representation of Acta, there are no let statements, which means that the lets are inlined, which results in duplicate computation, which made the Acta front end quite slow on programs that used lets. Similarly, the if statements weren't translated to be lazy evaluated, which also caused some performance overhead. But after rewriting the program so that they didn't use those constructs, we got similar comparable performance between Rocq and Acta front ends. Similarly, for the Lean front end, we also found that most we haven't identified all of the overhead for Lean on the examples, but the majority of it came from differences in standard library functions. So some of the standard library functions in Lean were very inefficient. And also the Lean backend relies heavily, well, not Lean backend, but Lean in general relies heavily on type classes. So all of the standard library is layers upon layers upon layers of the type classes for all operators and conversions between NAT and different types. And all of these type classes don't get fully erased. So you get sort of all these functions saying, go find this type class, which gets instantiated to this. And that adds a lot of overhead because so just to do just to compute 1 + 1, you need, I think it was 3 inductive types and 5 definitions, where you would expect it would only be 1 inductive type and 1 definition, an inductive type for NAT and a definition for addition. But you get a lot of overhead due to these type classes. Most of this overhead goes away if we mark all of the type class functions as being inlined and then do beta reduction. So after doing that, we found that most of the overhead for the front end disappeared. And then we have some, as I said, very preliminary evaluation of the backends. So we evaluated the C and malfunction backends against each other and found that malfunction generally performed better on the majority of examples. We also compared to the built-in Lean compiler, built-in unverified Lean compiler. It's not in the graph, but we have also compared it to that, and we found that, as expected, the reference counting from the Lean compiler does yield better results, better performance than OCaml. But on most examples, it's still within a factor 2 or 3. Even the very memory-heavy examples. And last thing I want to say, so as something that's relevant to, I guess, most of you, so we want to also in the future try using Peregrine to extract a verified EVN implementation with a verified cryptographic primitives. But this is still for the future. Now let's go ahead.
Yeah, super cool. I think it's really great to be able to connect so many front ends to all the work that basically took years to do in the past to get Rocq and all of the other infrastructure there to connect the different backends. So I think it's super cool work. I don't know if anyone else has questions. I'll maybe give a few seconds for anyone else to unmute or type something in the chat or raise their hand. Otherwise, I might have at least one and then try to not run over too much. Yeah, go ahead, Yoshi.
So the type system of Rocq is really aware about the denotation of terms, what kind of properties the values have when the input satisfies this property, the output satisfies that. This kind of thing, but it's not really aware about how many times things are used, and that's why in some backends garbage collection is needed. In some others, you keep allocating, and you don't free that. I guess that's the meaning of the bump allocator. And then I always wondered if there's meaning or reason to implement linearly typed proof persistent. And here, I guess I'm seeing a very good excuse, a very good motivation of doing some linear type thing in a proof persistent, so that the program extraction can utilize the linear type annotations to see when things are no longer needed and can be freed, so that maybe you don't need garbage collection at all, or at least you can rely less on garbage collection. What do you think about these kinds of directions?
Also, at least the preliminary evaluation of the backend shows that there is a good deal to gain from the reference counting that the Lean compiler does. We don't know we haven't identified for sure that that's the sole reason for the performance gain in the Lean compiler, but we expect that that is at least a significant part of it.
I see.
Yeah, go ahead, Guillaume.
Yes, thanks for the talk. I wonder, for the project to verify MVM implementation, you have more details yet about the injection will take?
Sorry, I didn't catch the last bit.
Yeah, do you have more details about the EVM verified implementation project?
I don't. Maybe Bas can say something about that.
Yeah, I can say a bit otherwise. Or Bas, obviously, you can jump in, but I think the short version is that Carl has this project to have a kind of canonical EVM specification in Rocq, and that's kind of getting close, or has essentially reached a first release of sorts, and then it's a matter of plugging that in basically into the certified completion pipeline and compiling it down to RISC-V and seeing what you get. I think Carl was talking to Bas about doing this maybe sometime in February, and then the work on that, I guess, is starting, and maybe Bas can add some detail here.
I think that's mostly correct. We'll wait for Carl to progress a bit more, and then we'll announce it.
But yeah, it should be a cool outcome.
Yeah, okay, thanks. And I had another question, but do you plan to add primitives, for example, in Rocq or Lean, to access to state manipulation?
That's not something we've discussed.
So one kind of quick question I had actually was relevant to the last talk we had last week, which was obviously porting some Rocq things to Lean that Bas was talking about with this is proof. Have you, by any chance, kind of took some Rocq code, maybe from proof or something else, ported to Lean, and then kind of compiled, done something to both of these, with Peregrine, and then compared, what the backend outputs are for both? That would be maybe a way to kind of test or differentiate test, the two front ends in some sense.
Yeah, so the only way we've compared the front ends are on these benchmarks that I showed. So these were basically written in one language, and then asked an LLM support it, just like Bats did with SS Proof to the other proof assistants. And that gave some mixed results.
Yeah. So it is quite interesting, I think, especially seeing, I guess maybe C being worse for. Well, I don't know enough about like what the Rocq looks like to get a sense of where the performance differences might come from and things like that. But it's definitely interesting to see the performance difference documented at least, and kind of seeing it if there's whatever kind of bigger programs can be tested would be quite interested, especially if there's some memory management issues. I expect they would show up in rather drastic ways on some bigger programs.
Yeah,
and I don't know how much of an effect I would see with Lean being intended for garbage collection probably plays some role in how it was designed, and I guess that goes back to Yoichi's question originally, but no, it's super interesting.
So the main thing is what Eske said already, is that the use of the standard libraries. So as soon as you start on as soon as you depend on the standard libraries, all comparison basically goes out of the window.
Yeah.
Just because they're implemented differently. Eske, you had some nice examples. Maybe you can mention them.
Yeah. So for example, we found that the power implementation in Lean is horrifically inefficient compared to whereas in Rocq and Acta they're sort of implemented the same way. Also, another thing that we ran into was in both Rocq and Acta, all arithmetics recurs in the first argument, whereas in Lean they recurs in the second argument, which then meant a huge performance difference, because then suddenly, if the second term always happened to be smaller, then Lean suddenly got a huge performance boost on a problem that should have been the same. So we ran into a bunch of these kind of problems.
Yeah, that's interesting, because it's kind of it probably points to just ways in which the standard libraries could be improved more than anything, which is actually a nice thing to document and to have kind of written down somewhere as well.
Yeah.
Okay, yeah, very, very cool. So I don't know if there are any final questions. Otherwise, I guess we're at about time, and so it's probably a good idea to call it. But yeah, this is I think this is really fantastic work and really useful to try to connect all of these things together. Okay, then I'll stop recording here, and then it'll be up on YouTube sometime this evening.